So do we start?
Yes, please.
Okay, hello everyone. Um, Today we're going to present the Green Commuter Project. Our team lead is Helen Argadona, along with our team members Dion Yu, Ryan Patterson, Fabiola Vasquez, and myself, Jack Tarsing. Our liaison from the Green Commuter is Gustavo Achiozo, and our faculty advisor is Dr. Michael Thorburn himself. Next slide. So we will begin with our agenda. So starting with our agenda, I will go over the project objective and background. Then Dion will take over the technology assessment and development. Brian will then discuss the vehicle state flow simulation. Then our team lead will cover the V2G Simulink simulation. Then finally, Fabiola will explain the data integration and cost analysis. And then it will go back to Helen, concluding everything together. Next slide. So the objective for our senior project was to assess the cutting edge technology and V2G technology and the opportunities it present to design a system where a green commuter could leverage V2G concepts to augment their business, specifically their electric vehicle fleet management and charging station installation verticals. And this project brought us the opportunities to investigate development of technology, capability for vehicles in the green commuter fleet, installation of prototypes, the evaluation of the whole green commuter location system, and the system study and design for forecast and assessment of technology. Next slide. Go to the next one. So to begin, let me offer some background information about our liaison company, Green Commuter. Green Commuter, it was founded in 2014. It's an all-electric van pool provider in California that combines van pooling, car sharing, and fleet replacement. In 2018, CEO Gustavo Achiojo established EV charging solutions under Green Commuter umbrella. EV charging solutions provide charging solutions to public, commercial, industrial, and multifamily properties. A fleet consists of many different types of cars, such as Tesla Model X, Nissan Leaf, EV Star, Chevy Bolt, and next slide. So vehicle to grid, what is V2G? Vehicle to grid is a technology that allows the electric vehicle to be used as a mobile energy storage unit. In other words, a mobile battery pack whenever needed. It allows the energy to be sent back to the power grid or to be used in other applications. There's many benefits of V2G, including demand shifting, peak shaving, and frequency regulation through bidirectional charger. Ergo, it can help balance the whole power grid system. Next slide. So this is the California duck curve. And this it has all the California loading patterns. This graph shows typical demand behavior depicted in the blue lines. Demand is low while people sleep, slowly rises as the people wake up, and peaks around noon. Then peaks again at 6 p.m., tapers off around 6 p.m. The demand in the day is met by solar power, hence load shaving. This means that generators are needed less during this time, and that solar power is meeting the demand. Then at night, generators need to work harder to meet the full demand. There can also be much overproduction of the solar power. As you can see in the figure, it is predicted that overproduction in 2020 compared to the actual demand in 2013 is 7 megawatts for California. Here's where the electric vehicles can help. They can store the overproduction and curtail the ramp that is seen when the sun goes down. Next slide. So moving on to the next section, starting point of assessment, the technology. So in the beginning, we first bidirectional level 3 chargers, that's what we were working on. We decided to study them along with the EV Star due to its large size battery and the open architecture of EV Star. We also studied different type of connectors, specifically level 3 chargers, which is most available to the public. From there, we moved on to studying the Tesla Model X adapter. We wanted to see if we can even do V2G with Teslas, because Green Commuter Fleet mostly consist of Tesla. They have a lot of Teslas in their fleet. So we wanted to see if that, but due to their closed architecture, we could not study that Tesla Model X as well. And their cars, just to go over some of the specification, like their EV Star, the battery size was 70 kilowatt hour to 95 kilowatt hour, and which ranges from 125 to 200 miles, whereas the Tesla Model X battery size ranged from 75 kilowatt hour to 100 kilowatt hour, ranging from 237 to 295 miles. Next slide. So from there, we moved on to another important part of our project, the battery management system. The battery management system monitors and manages the state of battery. It basically guardrails the battery from operating outside its safe operating area. It monitors its state. It calculates secondary data. It reports that data while controlling its environment, authenticating it and balancing it. So the manipulation of BMS is basically what allows us to, or allows the user to control what percentage of the battery they want to export out. Next slide. So from here on, Dion will take over the technology assessment and development with you guys. Thank you very much.
Thank you, Jagtar. Hi, my name is Dion. I'll be talking about the vehicle to grid device our group has been interested in. With vehicle to grid comes vehicle to anything. Electric vehicles are simply a battery with wheels. As California aims for a greener future, vehicle to grid is just a start. Through hardware, software, and service, this empowers people to do incredible things every day. I'll be explaining the hardware, utility regulation, software, and how we plan on implementing it. Next slide. As my colleague Jagtar mentioned, we researched several ideas on how to produce our own prototype of vehicle to grid. Our final idea was to look into other companies that have researched and developed this technology. We discovered a company called Nuvve, which has been developing this technology for years. We chose Nuvve to be our vehicle to grid as our hardware and energy management supplier for Green Commuter's charging station network. Due to their convenience, their main headquarters is located in San Diego, making it easier to communicate. This is the Nuvve PowerPort, Nuvve's first generation vehicle to grid device. It has met all the rules and regulations such as UL 1741, stating that the inverter AC to DC inverter must be bolted to the ground and not implemented into a vehicle, making it mobile. Next slide. Here's the AC versus DC configuration for electric vehicle chargers. As you can see, the safety regulation standard I've just mentioned, UL 1741. On the left, the standard J1772 does not meet, not Nuvve's model, does not meet the utility safety requirements. The inverter is mounted onto the vehicle, making it mobile. On the right, you can see that it has met the utility safety regulation, that the inverter is mounted into the charger and onto the floor, making it not mobile. Next. Nuvve is actually the software manufacturer for vehicle to grid, and the hardware implementation is done by Hitachi. Electric vehicles have been looked down upon because of their limited range and the time it took to charge. So why would I want you to discharge your vehicle battery and drain it while you're at work, when your real intentions are go to work and charge your car so you have enough battery to drive home and drive back to work the next day? Well, there's an incentive and you do get paid for it. Who doesn't like making passive income? Vehicle to grid puts the energy management back into the hands of people by turning their electric vehicles into mobile energy storage. Nuvve has rolled out a vehicle to grid program in Denmark, Copenhagen, and their research shows an average individual could gain $2,000 a year from vehicle to grid. Next. As I mentioned, Nuvve is a software company and they have created the grid integrated vehicle software. This software allows the user to see the power flow of their car, whether it is charging or discharging. It also does so much more. Their software allows you to schedule your charge, discharge, so the system can accommodate your battery for when you will leave. You can also tell the system when to stop discharging and focus on charging. It also has an emergency charge if your vehicle is currently discharging and you are needed somewhere else immediately or later. Next. Nevertheless, we also considered installing Nuvve's V2G device in our liaison's home, as he has a solar panel with an interconnection agreement with the city. However, we also needed more regulation approvals from his utility company, which would have taken months to achieve. Needing months to achieve these approvals, this idea would not have been ideal for our current project. Next. So now that we have picked our Nuvve charger and our vehicle preference, we will create a simulation to demonstrate what is happening in the vehicle side and charger. We have created a simulation to demonstrate the CalState LA load to see the effects it causes with vehicle to grid. My colleague Brian will now be talking about the vehicle state flow.
Thank you, Dion. Hello, everyone. I'm Brian, and today I will be telling you guys about state flow. All right. In this phase of our project, our team was advised by our advisor, Michael Thorborn, to create a state flow diagram in MATLAB. The reason for this was because with state flow diagram, we were able to see various states of the vehicle and charger, identify different parameters and conditions for the change of states to occur, and how the user input affects the system. To make the To make the state diagram first, the team had to come to an agreement on a couple of things. Those things were the vehicle we based the simulation on and the conditions and parameters on which the V2G is activated in the vehicle. The vehicle decision was easy to agree on. We chose the Nissan Leaf since this is the vehicle our liaison wants, and it was easier to get information on the vehicle. The condition on which V2G is activated took some effort to come to a solution. At first, we wanted V2G to activate whenever the grid needed help, but with the allotted time, we couldn't come up with characteristics of the grid for the diagram. In the end, we chose to have V2G activate during the time interval at which there is a strain on the grid. That time interval is from 3 p.m. to 9 p.m. This made things easier in creating the simulation since the conditions on which V2G is activated is dependent on the state of charge in the vehicle and time of day. Next slide. This is the complete state flow diagram. The main thing I want you guys to notice is the two overall states or superstates called vehicle and charger. They have dotted lines instead of solid lines. This is because they are parallel states, which means they will run at the same time. This is what we want because we wanted the diagram to simulate real-life situations between the vehicle and charger. Next slide. Here is the charger diagram. It has the handshake controller state in which it's gathering information such as time of day, the state of charge of the vehicle represented by SOC. For the Nuvve app, the charger gets the user's input on what the stated charge level they want their vehicle at. That is represented by a desired SOC, and how long the user wants to charge their vehicle. That is represented by DCT. Once DCT is achieved, the vehicle stops charging and is ready to be unplugged by the user. The other three states are when the charger is giving energy to the vehicle, when the charger is giving energy to the grid, and when the vehicle is unplugged. The lines of code in between each state are the conditions to go from one state to the next. Next. This is the vehicle diagram. Here you can see when the vehicle is charging, discharging, or unplugged. And again, the lines of code in between each state are the conditions in which to go from one state to the next. Next. In summary, we learned the various states that the vehicle and chargers go through to achieve V2G based on the conditions we created. However, the main thing that can be done to improve the model is to create and implement the characteristics of the grid to the model so that it gets a better understanding on how the grid affects the system. Next. Now our lead Helen will tell you about our V2G Simulink simulation.
Hello everyone, I will be discussing the 24-hour simulation of the vehicle-to-grid system. We decided to move from the stateflow simulation to Simulink because it provides us an opportunity to do an analysis with the load system. This simulation was provided by MathWorks. This includes a photovoltaic farm, a wind farm, and a diesel generator on one side of the transformer. The other side of the transformer includes the V2G block and a load block that consists of the industrial and residential loads. This simulation outputs an array of the energy usage for every second within a 24-hour time frame. For our simulation, we have removed the photovoltaic farm, wind farm, and industrial load. To do this, we had commented out the blocks with their respective variables within the simulation. We modified the simulation to show us the data for the new system created. The first system we will look at is a diesel generator, which also represents the power grid. Under the mask of the diesel block, we are able to see how the system works. The system outputs a three-phase power called A, B, and C, as seen on the right bottom corner. They are also named 1, 2, and 3 respectively. This system also demonstrates the power and charge this block creates on the right upper corner. We use the diesel power for our data. You can see this variable next to the green diesel scope on the right upper corner. Now we will talk about the load block. Under the mask, you can see where the industrial load and residential load is located. However, we do not consider the industrial load data for our simulation. We did this by commenting out the output power variable so it does not affect the system. We only use the output data for the residential load, or also known as the calcitolet load. Here, we are looking underneath the mask for the V2G block. This system is a three-phase power with the effects of the charging and regulation of the vehicles. We can see the input of the three-phase power on the top. As you can see, this system has two parts. The left is the regulation side and the right is the charging side. Charging occurs when the grid gives power to the electric vehicle. Regulation occurs when electric vehicles give energy back to the grid. The important variables we take note of are VAB and VBC above the voltage measurement blocks. These variables are inputted into the V2G system, which outputs the IA current and IB current. You can see these currents being inputted back into the three-phase power system right below the orange and yellow current blocks. I will show you how these variables are used in the next few slides. At the bottom corners of the figure, we can also see the output of power and charge for regulation and charging. Now we will talk about the car profiles block in the middle. Underneath the car profile mask, we are able to see the total amount of profiles. The simulation came with 5 different profiles. However, we commented out 2 and modified 3 of them to represent the different types of students attending the campus. Here we take a closer look at what kind of profiles we're looking at and the overall vehicle parameters. On this picture to the left, these are the parameters the V2G block needs. It consists of rated power, rated capacity, and system efficiency. These parameters are chosen to represent an ideal Nissan Leaf with V2G compatibility. Underneath that, there is also an option to turn V2G on or off. Below that, we also decide the amount of vehicles per car profile. For this simulation, we use 100 vehicles in total. On the picture to the right, we can see the 3 different profiles we have created. The first profile on the top represents a student who attends campus throughout the morning and afternoon. In the graph, the signal goes high when the vehicle is plugged in, and the signal goes low when the vehicle is not plugged in. In the first hours of the day, the vehicle is plugged in at home. Then it unplugs for about an hour on its commute to Cal State LA. Once it arrives on campus, it is plugged in again, and it is unplugged on the commute home and plugs back in once the vehicle is back home. The graph in the middle is the second profile, which represents a student who has only evening classes. The third profile represents a student who only has morning classes. Here we see underneath one of the car profile blocks. This demonstrates how we modify the simulation and how the changes affect the simulation. From left to right, the simulation starts at the time as an input. Then we are able to edit when students are charging their vehicles on campus in the state of charge initialization table and plug state table. These tables are inputs to the state of charge block and charger control block. Those blocks determine when the vehicle is either in charge mode or regulation mode. In this block, we are seeing the electric vehicles when they are charging. We can see the VAB and VBC variables in the left corner. The blocks use the parameters and voltage variables to convert it to complex power. Then the outputs are the currents on the right upper corner, IA and IB. In this block, we are able to see the grid regulation process. It is similar to the system when electric vehicles are charging. The inputs are VAB and VBC on the left. It then converts this to complex power, then the outputs are the currents IA and IB. Now we are able to see the amount of cars in charge and cars in regulation with respect to time. This result comes from running all the profiles together. In the left picture, we can see the cars are charging in the afternoon and evening. In the right picture, we are able to see that cars in regulation in the morning. Now, Fabiola will talk to you about data integration and cost analysis.
Thank you, Helen. Hello, my name is Fabiola, and so far we've talked about phase 1, the importance of V2G with respect to frequency regulation and how EVs provide a solution to California's Z-curve problem. We've also taken stock of the customer's inventory and assessed what vehicles would be ideal to implement V2G. And in phase 2, we explored the relationship between the vehicle and the charger and how one state of the vehicle depends on the other within state flow. This allowed us to figure out different conditions and parameters for each state. We then saw how we use Simulink to simulate the load within the V2G system and the grid. Now this brings us to phase 3, where we change load parameters with the Cal State LA data to formulate a cost analysis. Next slide, please. Now, I will walk you through the tools used in order to create a daily use load model for the campus, where the model was applied within the simulation, the DWP rates used to create cost analysis, and finally, the results. Next slide. I was tasked with applying the Cal State LA load data into the model. I used data given to the team by Brad Haydell, Cal State LA's Energy and Sustainability Manager. The data is seen on the left, which is the school's meter readings for the months of March 2019 through November 2019. This data is used along with the load models created by the CEC in their report, California Investor-Owned Utility Electricity Load Shapes. In this report, they outline 4 different load models specific to California college campuses for a 24-hour period, and they have one for each season. Next slide. The load models were then input into the mask residential load, which is actually the Cal State LA campus, as is seen on the bottom of the slide. Next slide, please. The outputs which we're most interested in were the vehicle loads, the residential load, the combined or total load, and the diesel power. Most importantly, we're interested in the cost of energy at low and high peaks, as well as the base energy charge. We created code that takes in the output data from the simulation and calculates utility cost. We used DWP's rates along with billing data also provided by Brad Haydell. Based on the billing data, we found that the school is categorized as a large commercial and multifamily service rate A3. Next slide. Here's a sample of the aforementioned code. Here, we're able to calculate the low peak costs, the high peak costs, base energy costs, and from that, the total costs. Variations of this code were used for all 4 seasons. Next slide. And here, we see the energy consumed throughout a 24-hour period. Firstly, the legend shows the vehicle load in yellow. This is the sum of all EVs in regulation and charging power consumption. I'm gonna start over on that. Firstly, the legend shows the vehicle load in yellow. This is the sum of all EVs in regulation and charging power consumption. The diesel in red shows the amount of power provided from the utility company. And the total load green, which is the sum of Cal State LA load and all EVs. On the left-hand side, we see that V2G is enabled, and on the right, V2G is disabled. On the left-hand side, we see that the EVs are taking power from the grid in yellow, whereas on the right-hand side, the EVs are flatlined at 0. This highlights an issue we encountered, where the EVs are simply disconnected from the load and are not giving power back to the total load. This is also verified by looking at the shape of the total load in green. It is much smoother on the right-hand side, no effect from the EVs versus the left, the green line, which has apparent ridges from the EVs loading effects. Ideally, we wanted to see the yellow line go into the negative side of the megawatt axis, indicating that it is actually giving power back to Cal State LA and reducing the load by discharging. The months September and November show the same pattern as is seen in April. Next slide. Here, we see that same pattern in September. The vehicles on the right are not connected. Next slide. And here we see the same pattern in November. The vehicles on the right are not connected. Next slide. Here, we're able to calculate the low peak costs, high peak costs, and the total costs for one day. Again, we see our issues highlighted in red, where the total energy consumed is decreased when V2G is off. But we saw that this was due to the fact that the vehicles were simply disconnected from the grid. We expected to see a decrease in consumed power when V2G was enabled, as the campus would pull energy from the vehicles and therefore reduce the load of the school as is seen from the grid. Future research should focus on this disconnecting issue in order to see the actual benefits of V2G and possible savings. Now, my colleague Helen will make some final comments and suggestions about our experience with the Green Commuter project. Thank you for your time.
Thank you. In conclusion, we were able to accomplish our first objective. We have researched various methods to implement V2G to the Green Commuter fleet. The technologies we looked at include the bidirectional charger, a Tesla Model X adapter for the charger, and a battery management system. We have discovered that our ideal vehicle to use for V2G is the Nissan Leaf for its current bidirectional flow compatibility and because our liaison has many Nissan Leafs in the fleet. However, all of these technologies are not ready for the market to use because of the current US V2G regulations. Those regulations will be ready in the near future. We were also able to accomplish our second objective. We determined what hardware to use, which is a Nuvve bidirectional flow charger. We picked a location to do our experiments, which is the liaison's home with the PV system. Once the installation is complete, we have planned to use various meters to evaluate our system. However, installing this would take various months of trying to get permission from the local utility, which is not within the senior design timeframe. We have also completed our last objective, which is to use a simulation to study and design for a forecast and assessment of technologies. The simulation needs to be improved so more regulation occurs to be able to decrease the power usage. Now we will talk about our experience and observations in this project. Our client, Green Commuter, is a startup company, and given that, we found that our customer was eager to break ground on V2G technologies. So we spent a lot of the first phase of senior design doing research. This took a lot of time, and most of our research was not used. We had tried to learn various different things about V2G. We were looking at it through a wide lens, and we needed a more narrow focus. Afterwards, the team was able to join a table business meeting at San Diego between Green Commuter and Nuvve, the company that owns the hardware that we have chosen. In this meeting, we learned about Nuvve's advancement in the V2G space. We also learned that the various regulations that prevent V2G to occur in the United States. In this meeting, Green Commuter also agreed to purchase Nuvve bidirectional chargers as well. As a result of this meeting, our requirements have kept evolving throughout the fall semester. Green Commuter and the team found that the technology was further advanced than what we had anticipated, and this had led to a moment of refocusing on what the senior design team can do to help Green Commuter. This is when we had decided to use a simulation and demonstrate how V2G can affect the load of Casa de Ley. This decision was made at the end of the fall semester. From this project, we have learned the real-world experience with working with startup companies. Decisions are made quickly, and pivoting the team's direction can occur in a matter of the day. The effect felt a little like whiplash from the quick changes in direction. Now we will talk about the next steps for this project. Green Commuter is waiting for regulation to allow for frequency regulation. So this leads to the reevaluation of the current project. It can be a new project implementing V2G technology on campus to make the campus more green. Or if the V2G regulation allows, it perhaps can be working on a Green Commuter vehicle to contain an inverter for bidirectional flow. We are not sure what can be the next project, but this will be decided for the next team and Green Commuter. As for the simulation needs to be modified to allow more regulation to occur throughout the day. This will allow for a decrease in load and will shave the Casa de Ley load. We also think that a new relationship with LEDWP is needed. It would be great for senior design team to work with DWP to validate or improve a cost analysis for Casa de Ley. Another option for this project is to develop a relationship with the Casa de Ley School of Business to improve the simulation to make Casa de Ley more sustainable. The College of ECST and Business has worked before to work on a project with the hydrogen stations, and we believe that this might also be a great project to implement on the campus. Now, our team would like to use the time to thank Michael Thorburn for helping us on the various times we had gotten stuck. Thank you for advising our team and helping us learn the various functions of MATLAB. We would also like to thank the Green Commuter team, Gustavo and Ian, for helping us learn more about their fleet and going above and beyond to communicate with Nuvve at San Diego. We would also like to thank Brad Haydel, the Energy and Sustainability Manager of Casa de Ley, for cooperating with us on creating the load model for the simulation. We would also like to thank everyone for attending our presentation. Thank you, and are there any more questions?
Okay, thank you, team. Very interesting presentation. We have plenty of time for questions. All you need to do is unmute your microphone and then just step up to the mic. Does anybody have any questions?
I guess first of all, I'd like to congratulate you. What a great presentation. I was just wondering, as your batteries in your cars charge up and discharge through the system that you're analyzing here, does that have an impact on the lifetime of the car battery as well? Or does that have a cost impact? Because that would impact your costs in the long run.
Yeah, so we have done some research on whether it affects it or not. And I believe there are some chargers that can allow for the depletion of batteries to, like, the life of the battery to decrease. But we believe that the Nuvve chargers they've used from their own tests, they have not seen the depletion of batteries. So the life would be longer.
Good. Well, thank you. Great presentation. I enjoyed being able to participate and listen in. Thanks.
Thank you.
Thank you.
Thank you.
Thank you.
Other questions? Let me ask the students then, given everything that you've done this semester, which part of it did you find to be the most interesting?
I'll go ahead and take a gander at that one. So I think at the beginning of the last semester, I was really curious just to see how far along the technology was, and kind of the secret that many companies didn't really want to release how far along they were, mainly because regulation it just isn't there. And the state of California is surely trying to be ahead of the curve with respect to being more green. But as far as the whole of the US is concerned, like just getting our government on board is really holding back a lot of research and a lot of companies. So I kind of found that like a really exciting place to really just be exposed to all of these companies just striving to, I mean, I guess lobby and just seeing the collision of government and company and research and really how that holds companies back, but yet they still have to be adventurous. So I thought that was very interesting.
Thank you, Fabiola. Anybody else?
Also, I'd like to say like what I found really interesting was like the whole idea of working with a startup company. And I mean, we learned a lot working through like everything can change in a day, as like Helen said in the presentation. Many of the times we're working on one thing and then our liaison wants to work on something else, so we would do that. So it's a really new experience of working with a startup company, and um, I kind of liked it too, and I basically, but I got to learn from it a lot. So I find that more interesting too.
Okay, thank you, Jagtar. Are there any other questions? Okay, if not, well, let me thank the team for presenting. It was a very interesting presentation. I also want to thank, Green Commuter was a member of the LA Clean Tech Incubator, and we've had a good partnership with them over the last few years. So I'd like to thank them for helping us meet and work with Gustavo and his team at Green Commuter. Okay, our next presentation will begin in about 5 minutes. This is going to be a lithium-ion battery management system presentation. As the team queues up, somebody will take over the screen.
Very much, guys.
Yeah, thank you.
Thank you.
Thank you.
Thank you.
Don't forget for everybody to fill out the Qualtrics survey and provide us some feedback. It's really important. Thank you. I don't see anybody here yet for the next team. I guess they're doing last minute preparations. We'll get going again in about 5 minutes. So just stand by, please. Don't go anywhere. Lots of exciting material yet to come. You can start whenever you're ready.
Good afternoon. Thank you for being here. This is Team 32, the Lithium-Ion Battery Management System, advised by Dr. Masoud Shaverdi. My name is Anel Nabilsi, and my teammates are David Almonte, David Diaz, and Patrick Dong. Today we will go over the background. Oh, next slide. Today we will go over the background, the objective, the system overview, system structure and design, the hardware, and the software. Next slide. Let me begin by giving you a little background about the lithium-ion batteries. Lithium is the lightest metal with the greatest electrochemical potential and the largest energy density per weight of all metals found in nature. Lithium-ion is a type of rechargeable battery that is most commonly used in electric vehicles and solar applications. Lithium-ion has a number of advantages compared to other storage devices. It is high power, high energy density, high efficiency, has long life cycle, and a low discharge rate. Despite all these advantages, lithium-ion batteries still require a protective device to maintain safe operation. Next slide. This device is known as the battery management system. A battery management system is simply an embedded system made of purpose-built electronics combined with software to enable a set of specific applications. Battery management systems differ depending on the application. However, the main task of the BMS is keeping check on key operational parameters during charging and discharging, such as voltage, current, and battery temperature. The monitoring circuit provides input to the microcontroller that determines the different states of the battery, such as state of charge, SOC. Most battery management systems, including ours, have a capability to isolate the battery from the rest of the system during fault. Well, when considering a battery management system, there are generally key specifications you should consider. I'll go over those on the next slide. Understanding the rapidly changing market, it is important to know the types of products available, their available features, and of course the cost. Here we have a table comparing our BMS to commercialized BMSs or off-the-shelf BMSs from different manufacturers. Well, what are the best trade-offs? In the end, it depends on your particular application and design requirements. But you'll see that in most cases, BMSs composed from inexpensive electronics allow for less reliable battery management systems, and BMSs that are built from higher quality electronics tend to be more expensive, but end up being more reliable and therefore extend the battery life. Now that I've given you a little background on battery management systems, let me go over some of the key objectives. Combining software and hardware of our system, our battery management system senses temperature, measures voltage, measures current, avoids overcharging, over discharging, communicates with the microcontroller, is able to detect any fault, and give us an accurate SOC. Now that I've discussed the background and the objectives, here's David Almonte.
So for this portion, I'll be going over the system overview, and our hardware requirements for our functional requirements for our hardware were for the hardware to be able to measure cell voltage, the overall battery pack voltage, and the overall battery pack current. The hardware had to protect the battery itself from over discharge and overcharge by opening a contactor, and needed to communicate with from the microcontroller to these sensors in order to protect the battery itself. The functional requirements for the software was to control the operations of the hardware by making decisions and estimate states for the sensors, to send signals to the contactor and control that, and give an accurate SOC estimation. Next slide. The performance requirements for our hardware was to be able to measure 5 volts for the hardware, and the current transducers needed to be able to measure at least 70 amps continuous and 120 amps pulsating. The temperature sensor had to have a range within negative 30 degrees to 55 degrees Celsius, and the automatic DC contactor had to be able to measure up to 24 volts and 200 amps DC. And as far as the software had to be programmed to measure the temperature range of negative 30 degrees Celsius to 55 degrees. Discharge a switch if it exceeded 3.6 volts, and update information for the cell voltage, the current, and the temperature. Next slide. So the capabilities of our individual parts, like the microcontroller, had to be able to analyze analog inputs and outputs and have a acceptable, reasonable processing time to that would send the signal, communicate with other external devices. The voltage sensors had to measure between 0 and 5 volts. The current sensor between 0 amps and 70 amps continuously. And the contactor had to meet the parameters of measuring 21.6 volts and 70 amps. And the temperature sensor, of course, like mentioned before, between 30 degrees Celsius and 55 degrees Celsius. Excuse me. The next slide. So we were given a budget of $300 for our overall project. We slightly exceeded that budget by, I guess, $37.10. Our most expensive parts were the current transducer, which was $130, and the DC contactor, which was $138. But overall, we came close to the budget, just maybe slightly went over. But we were able to buy quality parts that fit, that pretty much fit within the range of our budget. Next slide. So we had 3 phases. We broke down our project into 3 phases. The first phase was the requirements and the concepts, which we began with the scope of the project, did research on individual parts and the specs, and we estimated the cost of each individual parts. We came up with the requirements and the functional requirements and the performance requirements for our system. Shows the capability of each individual hardware. For the second phase of the project, we began by designing a block diagram of our system and creating a lithium-ion battery on a real-time simulator before we connected our system to a real battery. Our group started the SolidWorks design of the actual overall package, and we also began coding for the state of charge estimation for the battery. And for the third phase of the project, that's when we began to test the voltage, temperature, and current sensors that we had purchased, see if they met our requirements. We finished the SolidWorks version of we were wrapping up the final SolidWorks version of our BMS package, and we connected the sensors to the Raptor controller to make sure that the system would run the way that we expected it to run. Next slide. Here's a work breakdown structure. Our advisor was Dr. Shiverty, and he communicated to our team leader, and our team leader would break down each task and communicate to us as well. And our team leader was in charge of the software. David Diaz was in charge of the hardware, and Mel was in charge of the structural design of the project. And I was in charge of assembling the package. Next slide. And then here is a overview of our entire system. The voltage sensor connects in parallel with the battery. The current sensor is connected in series with the battery pack, and same for the temperature sensor. And the microcontroller converts voltage, current, and temperature from analog to digital. The controller was programmed to measure and display all the information to the user, and that would have been displayed on a small screen. Next slide. And then, excuse me, here is Amel to talk about the structures of the project.
Here is a SolidWorks sketch of what we had planned to be our final deliverable. Our design includes a microcontroller, a sensor, a current sensor, a temperature sensor, 6 voltage sensors, a DC switch, the A123 batteries, and the battery case. Everything sketched is according to scale except for the microcontroller. The microcontroller that we chose for our system was a lot larger than your typical microcontroller, although we still wanted to include it in the SolidWorks sketch. So that was the only item that scaled down. As for the wiring, we plan to wire the components using a 14 copper, size 14 copper wires. In the overall design and the layout, in the overall design of the package, we were able to meet all the system specifications, dimensions, and temperature limitations. So that's the only thing missing is obviously the actual final product that we weren't able to do due to COVID-19. But now that you have a visual of our final presentation of our final product, this is my teammate, David Diaz, to go over the hardware.
Hello, I'm David Diaz, and I'm talking about the hardware. So in order for our BMS to work, we needed to buy components. We needed a voltage sensor, a current sensor, temperature sensor, but we also bought an automatic DC contactor to help protect our batteries, and everything is connected via input to our Raptor controller. Next slide. So the voltage sensor, we bought 6 of these voltage sensors, each that can handle up to 250 volt input. To test out these sensors, we applied Kirchhoff's voltage law so we can compare both the measured values and the theatrical values. The voltage sensors, they send out a signal that to our microcontroller that can manage, so we can manage the voltage values. These voltage values are used to help calculate SOC within the microcontroller. Next slide. The current transducer that we bought can go up to 70 amps continuous, but if there was a fault that was to happen, the current sensor can detect the fault up to 120 amps for about 10 seconds, and it sends a signal to protect the battery. To maintain the battery cell within safe operation, we need to measure this current so the batteries don't lose its full value to hold the full power. We used Coulomb counting to calculate the SOC, and the current sensor is in series with both the power supply and the battery packs. Next slide. So the temperature sensor that we purchased was between -30 degrees Celsius and 70 degrees Celsius. It is responsible to measure the temperature of the battery because heat can really kill batteries. You can feel it on your phone as well. When it gets hot, that can potentially kill your battery. Sensors, the temperature sensor that we bought gave us the value we would read was a resistance value, so we had to build a circuit using KVL to get a voltage value. The resistance value is assigned to its temperature value in Celsius. So this temperature sensor came with the chart that showed us if the resistance value came out to X number, then the it is equivalent to this temperature. And if the temperature conditions were out of our range, the sensor will communicate with our microcontroller. Next slide. Next is the automatic DC contactor. So the contactor serves as a safety device to isolate batteries from the risks of the system. The contactor will disconnect from the load when limitations are exceeded. The contactor is connected in series with our batteries and is inputted to our Raptor so it can automatically send a signal to disconnect so the batteries won't get damaged. Next slide. So this is a circuit diagram of our final circuit diagram of what our system would look like, and if each value has its own input to our microcontroller, and then if you see on top we have our current sensor, which is connected in series with our contactor, and if you notice, there's a 9-volt additional battery that we connected to our contactor because the contactor that we had purchased only went up to 20 volts, but we needed, I believe, 25 volts to meet our requirements. So we needed to attach a 9-volt battery. And then at the bottom is our temperature sensor, which we also connected. We connected a 250 kilo ohm resistor, so it could read a voltage value between 0 to 5. Next slide. And this shows our test board. This is what we were able to complete, and if you can see, we were able to connect our temperature sensor to our microcontroller and our voltage sensors at the bottom, but because of COVID-19 we weren't able to finally implement our current sensor and our DC contactor. We have our power supply which is plugged into our voltage sensors, And then our voltage sensor is connected into, each current sensor has its own input, and the temperature sensor as well is connected to its own input. And when we simulate it, it sends all the information through a CAN bus, which is displayed onto our monitor and shows the values that we are trying to record. And next, my partner Patrick will be talking about software.
Hello, I'm Patrick, and I'm going to be talking about the software portion of our battery management system. In here, this is a block diagram of our software block diagram of our battery management system. We have the input is a voltage, current, and temperature. This will measurement from the voltage sensor, current sensor, and temperature sensor. And we have the output is a SOC, SOX, voltage, current, temperature, and also we have the output come from the thermal management, cell equalizer, and the fault detection. The controller gonna be receive the signal from the voltage, current, temperature, and they're gonna be convert the analog signal to digital signal. By using all that signal, we are programming the controller to estimate our SOC and also sending all the necessary information, VOC, SOC, voltage, current, and temperature to the display to CAN bus, and also the temperature going to be sending the signal to the thermal management block. Thermal management block going to be keeping the battery in the safety rank. If the temperature of the battery is too high, they're going to be turn on the fan. And if the temperature is too low and the heater going to be turned up, the cell equalizer going to be receive the voltage signal, and then they're going to be keep the voltage of the battery in the safety rank. If the voltage of the battery is outside of the rank, they're going to be sending the signal out to the discharge switch and then operate the battery. And also, again, the voltage, current, and temperature signal going to be sent to the fault detection block. And in here, they're going to be doing all the same job function of the thermal management and the cell equalizer. In case of any like fault management or cell equalizer is not working, during the COVID-19 and our budget, we don't have enough time and enough money to working on the thermal management and then the cell equalizer, also the XOX. In here, this is our MATLAB Simulink for our battery management system. In here, we were using the subsystem block diagram to build the Simulink for its current, temperature, and voltage. Like you can see right here, we have the block diagram for current, for temperature, and for voltage. And we also have the measurement block. This block is going to be measuring all that signal and then receive and monitor the real-time measurement of the voltage, current, temperature to the display. This is what the Simulink block diagram for the voltage. We have the analog input. By using the dataset of the controllers, we can select the input number we want. Like you see right here, I will select the input 7 with the put up down is 681K put up, and the rank of that input is from 0 to 5, and the full analog digital count is 4095. In here, in this block, the controller gonna be automatically convert the analog signal to the digital signal. So that's hard for us to measurement to display the value. So we have another block is called the digital to analog converter. In here we're gonna be convert from the digital signal back to the analog signal by on knowing their minimum and maximum analog digital count. Also, we have another block is called a comparator block. This block is using for the fall detection one. So if any the battery voltage is higher or lower than their range, so that the software will be display and tell the user and let the user know is have a happen with the battery. Because at the beginning of the plan, our team plan using the 6 battery and they all connect in series. So at the end, we have to adding all of them together. This is the block diagram for the temperature. Same thing, we can select the analog input for the hour temperature. And in here, we are using the input 14. We will select all the input which have a same put up and put down, so that have us easy to convert the digital to analog. In here is how we at the measurement in the hardware section, we using the KVL to send in the voltage of the temperature into the hour to our controller. But the data sheet given us is between the temperature between the resistor and the temperature. So we have to convert the voltage temperature back into the resistor one. So this is how we program to convert the voltage from temperature sensor to the resistor. And in here MATLAB function, we using the interpolation. By on knowing the resistor and the temperature, we can using the 2D lookup table to telling the software at what resistor they're gonna be sending what kind of the temperature at that time for us. Because we normally working with the Fahrenheit mode, so it's hard for us to rigging the Celsius one. So in here we decide to add in another agile one is called the Celsius to Fahrenheit, and this is a equation how we convert it. And this is the current block diagram. At something in here at something we using the different we using the analog input. And then we have to convert this one from the digital signal to the analog signal. And right here, this and the current sensor is sending the voltage of the current there, and also we have to convert it back to the current. By on using the current sensor of the data sheet, we know what is the range of the current sensor. So from there, we can convert it by using the very simple map. Mathematical to convert from the voltage of the current sensor to the actual current. And this what go inside of the fall detection block. At beginning, like I say at beginning, the fall detection block is gonna be receive the current, temperature, and the voltage, and they're gonna be checking all and the curve, and they're going to be checking all of that. They have to make sure all of that value is in the safety range for the battery. And in here, this we using the compare to the constant. And right here, this is the function. This is MATLAB Simulink function for the voltage comparator. So we receive the signal. We telling the signal. If the voltage of the battery higher than 3.6 volts, it's going to be sending the signal, the digital signal out. And if the voltage less than 2 volts, it's going to be and it also have to send the signal out there. And this is how our digital output block look like. And David Almonte is going to be doing the conclusion.
Oh, so next slide, I'm sorry. In conclusion, we were able to complete the design of our battery management system. We completed the design of the circuitry for the system, the hardware portion, the software portion, and the SolidWorks model for the package was completed. We were able to test the voltage and temperature and monitor the measurements in real time on the Raptor Cal software. The very last step that we needed was literally to put the parts in the package, but due to COVID-19, that was the only thing that we did not do, but we did complete the entire design of the system. Next slide, please. And then here is a video of our actual system. The power supply is supplying 12 volts to the controller. The voltage sensor is connected. Oh, there's the microcontroller, excuse me. The voltage sensor is connected between the power supply and the Raptor controller, and the power supply is acting like the lithium-ion battery. The white pad was the temperature sensor, and here on the monitor, it displays the real-time measurements of voltage, current, and temperature. And if you look carefully, you can see the voltage will change from 1 to change to 1 when the voltage exceeds 3.6 volts. The battery pack voltage and the temperature measured are being displayed as well, if you look pretty closely. And that was the conclusion of our presentation. Thank you, guys. Are there any questions?
Okay, thank you very much. That was a very interesting presentation. We do have some time for questions. Who would like to go first? Just be sure to unmute your microphone before you start talking.
Let's see, I'll ask a question. This is Carl Salinas. First of all, it's an impressive amount of work that you guys were able to pull together. I'm really impressed with the quality of your block diagrams and kind of circuit analysis, system level circuit analysis, to be able to come up with essentially the operations concept of creating a lithium battery management system. In your test program, did you look at any like anomalous modes, things like extended overcharge or discharge, potential discharge modes or anything like that, thermal runaway? Was there anything on the kind of anomaly side that you guys looked at?
Actually, we don't have it during the COVID-19. At that moment, we are working. We are trying to send in actually not the digital output from the controller. We try to send in the analog output. But at that moment, and the school just locked down, and then we don't have time to testing it. So in the video, like we just showing them like let we go back to the video. Like we just have time to showing like programming them like to show the user like if any like voltage above 3.6, they're going to be sending out is they saying right here is a 1
Yeah, yeah.
They say, yeah, like when you
Right there.
see one right there,
Yeah.
so that means it have like the voltage is below 2 volt or above 3.6 volt.
Okay. Okay. Yeah, I'd sure like to see that, you know, as part of perhaps like a mini Monte Carlo or something like that, where you get a lot of data and you can begin to predict battery performance. I know this is a management tool, but that could be sort of an analytical side to the tool where you can then begin to see trends and, you know, the potential of failure mechanisms and things like that. But I think you guys did a good job with that. Okay, thank you.
You're welcome.
Other questions?
So I have just a short question for the team. So thanks for the presentation. Yeah, you guys did a really thorough job with the presentation. A lot of really interesting stuff. I was kind of curious. So let's say that the batteries, let's say that its capacity will decrease over time just because of aging. And so with the Coulomb counting, do you have a way to update the capacity of the battery as it decreases with time so that you can, you know, improve your state of charge estimation?
Yes. Like we spending the whole fall semester to working on the estimation of the state of charge of the battery. Like we know, like the Coulomb counting is a good method, but they also is not the accurate one. So we develop another software called command filter. Actually, it tended command filter because the curve VOC SOC of the battery is a nonlinear curve. So we have to use attended command filter. That helps us to improve the estimation of the SOC by on using the Coulomb counting and knowing the behavior of the VOC and the SOC curve.
Okay, very cool. Yeah, that makes sense.
Sorry if I add something. This is Masoud Shahverdi. The correct answer to your question, Dr. Bachman, is no. We haven't done anything like that. What Patrick is referring to is a state of charge estimation and, you know, very accurate way of SOC estimation. What you're referring to is battery degradation and how we can take it into account in the system. For that, we need to actually have a state of health model or any other degradation model involved. But the way that they implemented, that is going to be just model of a state of health, and then from there we can have battery degradation, and we can include it in Kalman filter way of estimation that Patrick is talking about. So short answer to your question is no, but we have something in place that we can add that later.
Totally makes sense. Thanks, Masoud. I wonder, I actually don't know much. I know I do more on the material side, less battery management stuff, but I'd wonder if you could ever see, you know, you'd look at kind of the cutoff voltage and you'd say like, oh, this time we counted this many coulombs, we hit the cutoff voltage, and that's, you know, 95% of what we got last time. And so you could kind of like update it based on the kind of the amount of charge you can get between your cutoff windows. I wonder if, I'm not sure if something like that's ever done.
Chris, I mentioned many times that you and I need to talk and work on this stuff. We have a lot of things in common. At some point, we'll do this stuff. But what you are saying is doable, but more accurate way is modeling. It's relying on a lot of tests on lithium-ion battery, because, you know, everything related to aging and degradation needs a lot of time for testing if you want to have accurate model. But what you are referring to is absolutely possible. That gives us at least a simple way of having some sort of understanding how it will be degraded. But if you want to go further and have accurate model, there are some model out there that you can mathematically tell how much of capacity you are losing, based on the throughput amp hour that you put or extract from the battery.
That makes sense. My one other quick question. I noticed your guys' battery voltages were like 2 volts. I was wondering is that actually like the kind of the voltage of the battery, or was I reading it wrong? Because it seems low for like a typical lithium-ion battery. Or maybe those weren't lithium-ion batteries in the test.
Oh, that's one for one cell only. At beginning, we want to do in the cell equalizer to make sure when we charge or discharge the battery or the cell is equal. So the one we showing on the display in there is like we protect at each cell, not the whole battery.
Gotcha. Seems even low for a typical lithium-ion battery cell, but maybe you guys have a little like non-traditional lithium-ion battery chemistry. At least typically the ones I know, like in your phone, are like between 3 and maybe 4.2 or something. But they make different chemistries with lower voltages. So you guys probably have some maybe like a little bit different one.
I see. Oh yeah, I got what your question. Like at begin of when we begin start of that project, Dr. Savardi suggest us using the lithium battery from the eco car and this very high battery. But like we have another team is a attractive battery characteristic, but by combining our two the budget of our two teams, we don't have enough money to working on that eco car lithium battery. So we go into the solution like we buy very small cell battery with like same A123 using in the eco car, but the very small one. So we can still working on that one. So that's why you see the voltage very small.
But Patrick, if you pay attention to Dr. Bachman's question, he's referring to 2 volts being low at cell level, and he's absolutely right. 2 is the minimum cutoff voltage at cell, right? And he's saying the nominal voltage should be around 3.4, 3.5, and something like that. And you know that stuff. So that 2 volt that you were referring to was a cutoff voltage, correct?
Okay.
Sorry, I'm going long.
We expired the time for this presentation. I hate to cut off a good discussion, but I'm going to. Out of respect for the next team in line. Let me thank the team, though, for a very interesting presentation. Obviously, one where the audience was quite interested in many aspects of it. So congratulations. Our next presentation is a gun zone disabler program. Do we have the team here? We need to have somebody from the team take over.
Yes, we are here.
Please take over the screen. You can share the screen and drive the charts.
Go ahead, Robert.
Let me ask everybody to remember that we've got a Qualtrics survey. So by all means, fill out your thoughts about the last presentation and keep the survey in mind as you're watching this next presentation. We appreciate your feedback. And without further delay, let me welcome the Gun Zone Disabler team.
Dr. Thorburn, can you hear me good?
I can hear you fine. I don't see any charts though yet. There. Okay, perfect.
Did you see the screen? Yeah, we can see it, man. All right, nice. Let me go to the front there.
Hello everyone, my name is Cecile Monroy, and today we are presenting our Project 62 Gun Zone Disabler. Here with me are my colleagues, team members, Jesus Ramirez, James Arredondo, Roberto Ramos, and myself. Our faculty advisor for this project is Dr. Avery, and our liaison is Professor Johnson from the Department of Criminalistics. Next slide, please. So we're going to be talking about the background and statement of work. Slide, please. So in recent years, there's been a growing number of mass shootings, and the AR-15 has been found and used in over half of those shootings, and that's the main reason why we decided to work with this rifle. Next slide, please. So for our statement of work, we just wanted to design a mechanism to prevent the firearm from firing in a predefined gun-free zone. And in order to do that, we decided to work with the global positioning system, it's a GPS, to locate the firearm. Once the firearm was located and found to be in a gun-free zone, basically the servo drives the linkage mechanism, which then moves the blocking piece to block the trigger. Next slide, please. And now I'm going to be going over the system requirements. So as you can see here, there's 6 system requirements, which are the battery life, adaptability, the cost, the GPS, and safety, as well as actuator efficiency. For the battery life, we have planned it to be a 6 months life standby and 9+ hours in operation for the 9-volt battery that we used. However, we were not able to do this due to the current pandemic, not able to perform that testing. The adaptability, it was minimal. We wanted to be minimal retrofitting, and we were actually able to fit all the components into the AR-15 stock and lower receiver. The cost, we had a limit of $300 that we wanted to stay by, and we ended up spending less than $200. The GPS, we just wanted it to be able to detect our working operational area, specific areas such as a house, a building, and then so I complied with that, and that was successful. For the safety, the firearm, we just wanted it to be made inoperable. When you try to break it down, tamper it, or disassemble it somehow. However, when we were not able to get done with that testing, as well due to the pandemic. And the actuator efficiency, we wanted to, the driving mechanism, we just wanted to choose that in order so it was well within the confinements of the 9-volt power supplied, and that was successful as well. Next slide, please. So up ahead, Jesus Ramirez, my colleague, is going to talk about the electrical engineering design process.
Hello. Hello, everybody. My name is Jesus Ramirez, and I was in charge of the electrical design process. For designing ideas for electrical components, the first design idea was to control servo motor to drive the linkage mechanism. The second design idea was to design and implement a GPS system that will locate the location of the rifle. Next slide. Now we're going to move over to the global positioning system, or also known as GPS. The reason for using GPS is since it offers a more controlled approach for keeping track of the location of any firearm compared to other signals such as Wi-Fi and Bluetooth. The red outline you see in the image represents the desired restricted zone. The black square represents a buffer zone. The buffer zone is used since many locations like schools or any other building have irregular shapes. Therefore, the buffer zone will help shape the zone better. Also, by using a buffer zone, it will allow the system to maximize the safety of that particular zone, since firearm will be disactivated before it has entered the red outline. Next slide. Now let's move into the electrical components. These electrical components were needed to satisfy the GPS system. The first component I want to speak about is the Adafruit Ultimate GPS Receiver. The Adafruit Ultimate GPS Receiver was selected since it offers a GPS model that gives precise and sensitive coordinate tracking. Also, the module can track up to 22 satellites on 66 different channels. This is important since this GPS receiver has the capacity to have up to 10 location updates a second. Next, the SparkFun Redboard. The SparkFun Redboard is a modified Arduino Uno for GPS-based projects. Next, I will be speaking about the SparkFun antenna board. The antenna selected from the antenna board was called GPS ceramic chip antenna. The specs would include frequency range up to 1.575 gigahertz, and it has a max gain of 3.4 dB at its peak, and it has an efficiency of 85% at its peak. Next slide. The next component was the 20 kilogram digital servo motor. The servo motor was selected to drive the leakage mechanism. The last two components were the 9-volt battery to supply power to the breadboard and the LCD screen, which was used only for testing purposes. Next slide. Now, in the image seen, we can see all the electrical components set up ready for testing. Next slide. Next, we will go into the system flowchart. Once the system starts up, the system will block the mechanism automatically. Then the location will be found if the location will be found. If the location can't be found, then the system will become locked. If the location is within a restricted zone, then the firearm will remain blocked. If the location is not within a restricted zone, then the firearm will be unblocked. The system will proceed to continuously check the firearm's location at specific time intervals. These time intervals were selected in order to help provide more power, to improve the power efficiency. Next slide. Next, we will dive into the code. First, we have the array. The array consists of 4 different predefined gun-free zones. 4 different zones were picked to have different testing locations. The presentation will be focusing on zone 4, which happens to be my house. Next slide. Next, we will look into capturing GPS coordinates. The lines of code presented, the lines of code present how the program will receive the coordinates from the GPS receiver. Let's pay attention to line 3 of the code, which says char c is equal to GPS.read. This line of code will get the coordinates from the GPS receiver, and the remainder of the code will confirm that the coordinates have been received. Next slide. Next, we will look into how the program is able to know that the GPS receiver is working properly. The 4th line of code has if, open parentheses, GPS.fix, close parentheses. This line of code will ask after 1 second if GPS is fixed. Being fixed means that the GPS is connected to 3 or more satellites. This is important since in order to get accurate readings, the GPS needs to be connected to at least 3 satellites. Next slide, please. Next, we will look at the if-else statements. In this part of the code, the predefined coordinates found in the array will be compared to the coordinates captured from the GPS receiver. If the locations match, then the system will disactivate the firearm. Next slide, please. Next, we will see the testing results. These testing results were obtained when testing inside of my house. We can see clearly in the images that the system disabled the rifle. If we see the image to the left, we at first see that from the serial monitor from the Adreno shows gun enabled, and then it changes to gun disabled. If we go a little bit lower, we see something called the zone change. This is very important because if GPS is moved at any given moment, it might be confused about if it happens to be in a restricted zone or not. So then I apply a zone change verification where it's going to check up to 4 different times to make sure that the coordinates received are actually disabled. As we can see in the following lines, that it keeps saying disabled. Next slide. Where are the images? Next, we will see the test results obtained when outside of my house. From the images, we can see that the system enabled the firearm. For this particular testing, I went ahead and stepped outside of my house to a little park where I live. And once I got to the park, I realized that the LCD showed gun enabled, showing that I was outside of the restricted zone. Next slide. Next, James Arredondo will be discussing the mechanical engineering design process.
Okay, so good afternoon. In order for the first part of this design process, the research was done into the laws And there were laws and regulations which prevented us from actually creating a functioning firearm. State law required us to seek approval from the California Department of Justice, and Cal State LA regulations prevented us from manufacturing and possessing a firearm on campus. There were options of airsoft guns and other replicas. However, the internal components were a lot different from an actual rifle. Therefore, the solution was to create a custom AR-15 lower receiver, which would suppress features that we wouldn't need, such as the magazine well, but would still function as a good model for our prototype. So research was also done into, next slide, into other types of existing models, such as the Armatix IP1 smart gun, which is the first commercial smart gun. And this one worked by using an electromagnet to block the firing pin. It required the user to use a watch, which communicated through radio frequency identification to the gun in order to allow it to fire or not. A similar concept would not work with this design, however, since radio identification would not be used, we would be using GPS. Research into previous senior design teams project was also done, and they utilized a trigger lock mechanism through the use of a solenoid that was required to be on. It's attributed to power consumption issues, as well as a 10-second delay to block the trigger. 10 seconds is a lot of time. Therefore, one of the objectives behind this project was to kind of speed that up. The idea of a linkage mechanism did follow through into this year's design, into the final concept that was thought up. Next slide. So there are three major components of an AR-15 for this project that was looked into. The stock, the grip, and the lower receiver. The buttstock and the grip are hollow pieces on a rifle, which helped address the concern of storage and how much space we had to work with. The lower receiver is a part of a rifle that houses the trigger components and would be used to also house the blocking mechanism itself. Next slide. So there were various different design ideas throughout the course of this project. As you can see, the green arrows will actually point to where the edits or the obstructions would be placed. The first idea was a firing pin obstruction, which would require a steel rod to stop the firing pin from moving. Another idea would be a barrel blockage, which would stop a bullet from being loaded into the barrel. And then there was disabling the trigger, which by stopping the trigger would actually prevent the gun itself from firing. Next. Okay, so these different design ideas, there were different factors that were looked into for each one, and each of these factors were awarded a point between 1 through 5, where 5 would be the most problems, the most difficulty, and 1 would be the simplest solution that had the less amount of issues that would arise later on. One of these would be size constraints, the amount of space we'd have to work with in order to achieve the goal. Another thing would be manufacturability. As previously stated, size constraints, the amount of space we had to work with was a problem. So how difficult would it be to manufacture these really, really small pieces, and as well as the complexity behind each design solution. The cost of implementing the overall design, cost of manufacturing. The difficulty issues would be the difficulty in the actual placement and the issues that would come from it, such as the firing pin, which is a moving component in a rifle, as opposed to the trigger. The trigger, for the most part, is stationary. It rotates about a point, but in comparison to the firing pin, it's a lot easier to stop that motion than to stop the firing pin's movement. The barrel is a pressure-bearing part, which means there's a lot of safety concerns for the user themselves. If something were to go wrong, messing with the barrel, it could cause damage to the user. The adaptability, there are many different kinds of firearms. Previous models focused on a handgun. We were focusing on a rifle. all these weapons are different and each carries its own set of challenges for stopping certain components. The idea behind this project was to adapt the mechanism itself into other kinds of firearms with as little modifications as possible. Here, the total values were tallied up, and at the end, the barrel blockage seemed to be the idea that would carry the most difficulty in implementing, and disabling the trigger was the easiest, the simplest solution. Therefore, that was the idea we chose to go forward with. So now I will pass it on to Haseen, who will go over the final design overview.
So for the final design overview, ultimately we decided to look at the mechanism of the trigger, and we see that when applying the force pulling the trigger, it causes induces a pivot around the pin, and then when preventing the pivot basically disables the trigger. So when disengaged, trigger is pulled. When engaged, trigger is blocked successfully. Next slide, please. So as you can see here that when the system is engaged, the sled is pulled back by the linkage servo, activating the linkage mechanism, which pulls back the blocking mechanism. And when it is disengaged, the trigger is successfully allowed to pivot around the pin. Next slide, please. So this is some of the stuff we printed out, and it's just a prototype. And you can see the locations here when the sled is moved and when it is engaged and disengaged as well. Slide, please. So here is the thumb hole stock, and this was custom, and it was made to hold all the electrical components which were measured. And as you can see, here is also included the servo as well as the linkage mechanism, everything together. And for the linkage mechanism, we were able to see that all the lengths and the angles are known, and the angle of rotation we were not able to come up with that, as we had planned to do some physical testing with the model, but weren't able to do so due to the pandemic. So the housing, the thumb hole stock basically houses a breadboard, the battery, the controller, antenna system, the servo, and the linkage. Next slide, please. And then Robert is going to talk a little more about the risk analysis.
Robert, you're muted.
Sorry. One of the last things we did for our project was risk analysis based on the problems we saw with our original designs, and we also listed out a mitigation approach we would take to solving these problems. The table below takes into account some possible risks, the impact the risk would have on our design, and the probability of each risk happening. So we assigned a number for each risk and impact between 1 and 5, where 5 would be the greatest, will be a bigger impact and bigger probability of the things happening. So a lower number would be better. The first thing we considered was battery depletion. The battery dying would have had a large impact on our design, so we gave it a 5. The probability of it dying was also pretty high, so we had to take that into account when thinking of the mitigation approach. The mitigation approach for this was to disable the gun once the system read that the battery was nearly dead. The second thing was the removal of the mechanism. Removing the disabling mechanism would have made the firearm into a regular operable firearm. The probability of this happening was high, as was the impact. Our mitigation approach would have been to make the disabling mechanism an integral part of the trigger system, meaning that removing it would have rendered the gun inoperable. The third was damage from the environment. Guns are used by people regardless of the weather, and since the system consisted of electrical components, we didn't want some water to get in and damage those components. It was also given a high impact and high probability number, since, like I said, it would have been likely for us to use out in harsh weather. So to mitigate this, we decided that all the electrical components would be housed in the stock of the rifle in an enclosed sealed compartment. The last risk factor was electromagnetic interference. We didn't want somebody jamming the GPS system when they were in a restricted zone, which would have made our design useless. So the mitigating approach was to completely disable the gun when there was no GPS signal found. So this next slide shows a table that had reevaluated the risk factors after applying our mitigating approaches. Keep in mind that many of these things weren't unfortunately implemented because we weren't able to meet up and work on it together. So for battery depletion, there was still a high probability of the battery dying, but the impact would have been negligible, as you can see on the column on the far right. For mechanism removal, we didn't get around to make the parts properly, therefore it's still a high probability and still has a high impact. The difficulty from implementing this came from the fact that retrofitting existing designs meant that all we were doing was adding extra parts to an already tried and tested mechanism. So the system would still have been susceptible to environmental damage, but we felt that enclosing it the way we did would have helped mitigate some of the probability and impact. And finally, disabling the gun when there was no GPS signal would have eliminated the risk of someone tampering with the GPS signal. So this next slide shows the risk analysis, but it gives us a visual representation of it. The table on the left just lists out the risk and the assigned shapes, where the solid shapes are the original impacts and probabilities before mitigation, and the outline shapes are after they were adjusted. As you can see, originally all of the risks were in the red, meaning that they were pretty substantial and very likely. After applying our mitigating factors, or mitigating approach, I mean, as you can see, the impact and the probability decreased for nearly all of them, except for the mechanism removal. And next, I'll move on to the conclusion. In conclusion, we were able to write code that moved the servo motor. We were able to make a GPS system that obtained the coordinates and specified whether or not you were in a gun-free zone or a zone where it was okay to use a gun. We designed a prototype of the LoRa receiver and the disabling mechanism, and it was manufactured using 3D printing. And in addition to that, we also designed a stock, which enclosed the electrical components. One last thing is acknowledgements. We'd like to thank Dr. Thurborn for helping the EE with guidance, Dr. Castillo for letting us use the 3D printing lab, Dr. Avery for advisement and guidance, Manny from the Firearms Reference Library for letting us mess around with the guns. And we also want to thank a few students, Helen for 3D printing, Eduardo Stavala for helping us with SolidWorks, and Alex.
And I would personally want to thank Alex Maxwell for helping me out with the coding and testing. Working on this rigorous code by myself was very scary, and Alex Maxwell really came in as my classmate to help me out with the coding and the testing.
And that's it. Questions?
Okay, thank you. It was a good presentation. I appreciate the work. I wanted to ask a question. Did you talk about the antenna system in the presentation?
I just spoke about the GPS receiver more specifically.
Right. Did you talk about, or did you look at any different antenna configurations to support the GPS receiver? Or are you using a built-in antenna on the system?
I tried both. I first tried doing a built-in antenna, but I found that the dB and the frequency range of those antennas, they were reduced compared to an exterior one. And since I was worried that all the compartments were going to be enclosed into the stock, I wanted ahead to use a little bit more powerful antenna, higher gain, higher frequency, and higher efficiency. So I went ahead and used an exterior antenna instead of the onboard antenna.
And how is that going to fit inside the pistol or the rifle?
If we go back to can we go to the stock, Roberto? Right here, if we see the green happens to be the GPS receiver. No, sorry, the green happens to be the board, the Arduino board. And the two light blue happens to be two breadboards back to each other. So on one side of the breadboard, it's gonna have the board attached to it. And on the other side of the breadboard, we're gonna have the antenna and the GPS receiver attached to that side. And the wiring is gonna hold it together as well.
Okay, thank you very much. Are there other questions? We have time for some questions.
Yeah, this is Carl. So that's quite an elegant solution, but did you guys, did you have any trouble with the GPS footprint? I guess I'm trying to understand is how accurate can you establish a boundary, and if someone's sitting on the edge of the boundary, what does the software do? Does it have some sort of logic that determines whether you're in or out, or did you guys test that out at all?
Yes, so if we go to the buffer zone, can you go to the buffer zone, Roberto? So in order to maximize the accuracy of the coordinates, I went ahead and picked the top left corner of the buffer zone and the bottom right corner of the buffer zone. And I used those coordinates to help me pretty much have this buffer zone. And when we talk about the GPS receiver, there are some limitations depending on how accurate the readings could be. And that really honestly depends on how expensive the GPS receiver is compared to others. Because the one that I chose wasn't too expensive, but the qualities of it was the fixed operation that I talked about in the code, that it's able to let us know when we're testing. It has an onboard LED light that allows us to know if the GPS receiver is actually able to connect to satellites or not. And we know that by the blinking. If it blinks every 5 seconds, then we know that the GPS receiver is actually collecting data from the satellites. But if it's more than 5 seconds per blink, we know that the GPS receiver is struggling to capture these coordinates.
Okay.
And that was a big benefit of why, because I started off with another GPS receiver, but the other GPS receiver would heat up a lot. It had a lot of heating issues.
Yeah, it's a lot of processing. If you're processing the data from 3 satellites, you're crunching a lot of numbers there.
Yeah, so I went ahead and investigated a little bit more expensive GPS receiver that helps with the heating issues and at the same time offers that fix on the board to allow me to know if the program is the one that's wrong, or if it's the actual component, the electronic component, that's having a hard time capturing the coordinates from the satellite.
Okay. Just out of curiosity, did you guys do any kind of weight analysis or mass analysis to estimate how much additional mass you were going to be adding to the AR platform?
Robert?
And we figured that the weight we'd be adding would be pretty negligible, since people tend to slap on like accessories to their rifles.
Yeah.
So we were kind of like, this wouldn't add too much weight to it.
Okay.
But overall, we didn't really consider that.
Yeah. Yeah. Well, I mean, I wouldn't think so, but it's one of those optimization things, I guess. If someone's really, you know, trying to balance this rifle or something, they might, you know, might have an issue with it. And then the 6-month battery life, did you look at your rechargeable battery, or was this just sort of use the battery once and dump it kind of thing?
Well, that was the next phase of the project, was to down the battery issue, but due to the pandemic, we were limited on those exams. Right now, the way the project is operating is simply plug in a battery once it's done, take it off. And I know that's not feasible, but due to the concern that's attacking the whole world, we had to, our time was limited to figure out that solution.
Yeah. Well, I guess I would give that, since this kind of gun is kind of more of a sporting thing for most people, you know, the idea that they'd have to replace batteries every so often probably isn't that big a deal. It might be different if it was kind of a law enforcement thing or some other, you know, official capacity where the person had to have it at the ready. But, you know, given that most of this type of gun is used for sporting, you know, I wouldn't think it's a big issue. Just a couple of things. One is, and it might just be my display here, but I couldn't see page numbers, and that sort of complicated me trying to follow the story and write questions. And then the other is just as a kind of a future, every time you present code and try to talk to it, that's real tough on the audience. So I know that you had to go through it to try to show us what you did, but next time you might want to think of creating more of a graphic, more of a pictogram to demonstrate what the code is doing, and then, you know, kind of reference the code very sparsely, because trying to follow code, even if it's just a few lines, is sometimes real difficult for audience members.
Okay, thank you for that.
Yeah. Good report though. I like the work you did.
Thank you.
We have a few minutes for another question.
Oh, go.
I have a question. It is really good that you guys mentioned the project from last year's Expo. I was there in attendance myself, and it was definitely concerned about the 10-second buffer for the gun to be disabled. I'm not sure if you guys mentioned an improvement of that buffer delay, if you guys dropped it down to like how many seconds. So can you provide information about that?
Yeah, we were able to cut it down a few seconds. It wasn't much, to be honest with you. We were able to only cut it down a few seconds.
Okay, all right, yeah, because on the slide where it has the, I think the electric design process, it was mentioned that you guys have used specific time intervals, but I didn't see any numbers. So I was just curious, like how do you guys improve the 10-second buffer delay? Because 10 seconds, like in the previous Expo, it was pretty long. You know, a gunman could have already shoot a person before the gun was disabled. So it was just my like question, like how did you guys improve that number?
Yeah, the GPS receiver offers, it's called a hot start, which allows us to connect to coordinates quicker. And this receiver has this hotspot part of its design, which allows us to get a quicker coordinates, and the quicker we get the coordinates, the quicker we could disable, we could deactivate the firearm.
I see, got it. Thank you.
Okay, well, that about wraps up the time. Thank you, team, for a very interesting presentation, and thanks to the audience for the interesting questions. Our next project is the optimal design and control of a hybrid PV and battery system. If the team's ready, you might start pulling yourselves together. If somebody can share their screen to drive the charts, and we'll get the presentation started in about 2 minutes. Not to add any pressure to the next team, but we've got 61 people in the audience at this point. This is our maximum for the event so far, at any one time. They must be anticipating a great presentation. Please remember, audience members, that we have a Qualtrics survey. I have posted that up on the chat room. I'll do that again right now, so that once you have listened to a presentation, It doesn't take just a few minutes you can do it on your cell phone. It's just a few multiple choice point and click type questions. We value the feedback. The students and I both value the feedback. Okay, if the team is ready to go, it's about that time. So without further delay, the optimal design and control of a hybrid PV and battery system. Go ahead.
Okay.
Your advisor just signed in, by the way.
Okay. All right, so good afternoon, everyone. My name is Jose Morales. I'm the team lead for optimal design and control of a hybrid PV and battery system. So today we're going to be presenting our overall project and what we were able to accomplish. And if you guys have any questions, feel free to ask at the end. So let's get started with the table of contents. So the introduction and background is going to be presented by myself, and then I'll be handing it over to my partner, my team member, Kajar Minasian, who will be presenting battery sizing and DPM, also known as dynamic programming model. And furthermore, after him, we will be presenting our control system, also called proposed hierarchy control, which will be presented by Ko Dang. And it consists of two layers, the top layer and the lower layer. So the top layer, as you can see, is going to be presented by Ko Dang as well. And the top layer forecasting is going to be presented by Axel Ochoa. As for the lower layer for our control system, it's going to be presented by Jose Rea. And that would include the lower layer forecasting and the simulation results of the whole control system. And in the end, to wrap things up, is going to come back to me where I would be presenting the conclusion. So let's get started. So I'm gonna give you guys a little bit of a background of our project. So we are working on the building called the Credits Innovation Center, located in downtown LA in the Art District. So that building was picked to meet the requirements of California's energy goal by 2030. So California's energy goal is to have 50% of the commercial buildings be retrofitted for net zero energy. So for the specific building we're working on, the energy demand is divided into two parts. One being the building and the other being the electric vehicles charging stations. So to give you guys more of an introduction, so the main goal of this project was to design an optimal control algorithm for the Credits Innovation Center, as you can see in the right. So some of the problems faced with this project was the load consumption. So from here on out to 2030, it's a big time span. So we know that the load consumption is going to be changing depending on different scenarios going on in the building. So also another problem we faced was predicting the load and sun irradiance. So predicting load and sun irradiance is pretty much impossible, but yet again, you got to find a way to get somewhat similar to what the accurate result may be. And lastly, the last problem is the electric vehicles. So as we know, electric vehicles are going to gain more popularity as we're all going to more environmental friendly use across the nation. So we don't know by how much the electric vehicles may change. So right here, we're going to be presenting the deliverables for this project. So some of the deliverables included agenda minutes, also as project updates, which were weekly. Also, we were, as you can see, we had our preliminary design review 1 and 2, which where we presented our just concepts that we would be using for this project. Some of them we discarded and some of them we kept. And as you can, also we have our final design review, which we're presenting today. Also, for our deliverables, we had forecasting data. So we had a lot of forecasting to do based on load and sun irradiance. So some include different models, some as dynamic programming model, also known as DPM, severe vector machine, also known as SVM, auto regression, also known as ARIMA, and PSO and GA, which are optimization tools. Based on what we got from our forecasting and we were able to find our battery size, we then had to contact manufacturers and receive a quote. just to present it to the customer and be able to have a plan where we have everything set, so just for them to purchase. So the project is pretty much organized, as you can see in the picture on your screen. As you can see, I'm the team lead, and then our team advisor was Dr. Araj. And the project was broken down into 3 main components, one being forecasting, other being battery optimized, and the lastly being our control system, also known as proposed hierarchy control. So as you can see, each team member at least worked with one of those 3 main components throughout the whole year. So now we have our work schedule. So our work schedule was broken down in the 3 semesters. So one being the fall semester. So that's where we mainly focus on theories and concepts that we may apply to help forecast sun irradiance and load. And then also we were able to determine which ones worked and which one didn't. So based off that, we were able to move on to our winter break, our winter break was mainly where we focused still on a little bit of research, but mainly started to develop our project overall. And in the spring semester, we were able to complete it. And as you can see, some of the tasks, we were able to contact manufacturers to see how much would it cost, despite the current situation going on right now. So as mentioned in the project organization, so the way the project was broken down was in 3 main components. One being forecasting, which included estimating the load and sizing the PV. So based off that, we want to know how much would be the load and the PV, because we're trying to expand every 3 years, starting from 2020, 2023, 2026, and to 2030. Next, based off that information collected, we would move on to a sizing of the battery. So the sizing of the battery, we would use all the information we got from the load and sizing of the PV and implement that to our dynamic programming model, also known as DPM. And then lastly, the last step is our control system would control the battery itself, which consists of a top layer and a lower layer. So what do we know for this project so far? Well, in the beginning. So in the beginning, we were provided with the information of the load and PV for the year 2030. This was provided to us by the grad students that we were working with hand in hand. We both had different tasks, our team and the grad students, but in the whole, at the end, we would combine the whole project and present it to the customer. Now I'll be presenting it to my team member, Kajar Minasian, who will be presenting a little bit more about the battery sizing and the dynamic programming model we use.
So I'm going to talk about a little bit about the battery sizing. As we know, it's a big part of our project because it ties down back to the actual PV system in order for us to achieve the net zero energy goal by 2030. Firstly, we have to find an optimal battery size. And we were able to achieve the goal by finding the optimal battery size and the optimum cost of it as well. We determined the cost and the battery using a dynamic programming model. And also that program optimizes the cost to, based on the lowest cost that we got, we determined the battery size. Next slide. Some of the inputs that we put into the DPM are as follows. As far as the batteries section of the inputs, it's the depth of discharge, the unit price of the battery, dollar per kilowatt, also the open circuit voltage, and the resistance of the charge and the discharge. We also included the number of battery cells in series. Another input that we used is the PV and the load profile of a whole year within 30-minute intervals. Also, the energy demand and the demand rates throughout the day, because LAWP has different rates throughout the day, because in the morning it starts off slow, and then towards the noon and afternoon, that's where it peaks and then slows down again. Based off those parameters, we're able to get a 720 kilowatt hour battery size for year 2030. So now I'm going to talk about a little bit about the DPM. DPM is a dynamic programming model. As I mentioned earlier, that's what we use to find the battery and the cost. We used it to find the optimal control problem, and based off of that, we were able to optimize the cost of the battery. Next slide. So this is an overall view of how the DPM works. Based off the parameters I mentioned earlier, we input it into the program and we run the program, and it starts calculating cost of each path. And after that, it picks the lowest cost for each path, and then it displays you the results at the end. Next slide. DPM is also a very efficient way to perform recursive computations, meaning it takes into consideration of the solution of the smaller problems of that instances as a whole to give you the solution. As far as our cost function goes, there are 3 different areas that we counted. One of them being the energy cost, which is you buying energy from the grid or selling it back to it using the PV system that we have, which in that case would be negative. Also, the second part is demand cost. The demand cost we calculate based on the peak power consumption of a month in 3 intervals. Also, we included the battery cost, which includes the battery degradation, because as we know, as time lifespan goes on of the battery, it starts deteriorating. Also, we include the operation and maintenance costs in as well to get a total cost of the battery. With all those in mind, these are the results that we got. The cost of installing the battery is about $183,000. The operation is about $47,000, and in total, we save about $194,000. On the right side, as we can see on the graph, it's a normalized savings graph versus the battery capacity. As you can see, as a battery capacity goes on, we save more and more. And for our project, the peak is about 720 kilowatt per hour. That's the maximum savings that we get. And after that, it starts going down. Next, I'll be passing it on to my teammate Kodang to explain the purpose of hierarchical control.
Good afternoon, everyone. My name is Kodang, and I'll be talking about what proposed hierarchical control is about. Next. So for our proposed hierarchical control is a 2-layer control system that controls the battery performance. So in our top layer, the top layer will optimize the state of charge, or your SOC, based on the long-term forecasting of the PV and the load generation for 1 week. And then the lower layer will optimize the battery based on the short-term forecasting of the PV and the load for 1 week. Next. So as you can see here, we have our flow chart for the top layer and the lower layer, which is all over flow chart for both layers. Next. So in the top layer, it will start by prompting the user to define the general parameters for the upper and the lower layer of the system. And then the top layer will import the GHI, load, and the battery data, and then send it to SVM, in which the SVM will forecast the GHI and the load for 1 week. After that, the DPM will run for 1 week, where it will give the SOC for every 30 minutes. And then it will check to see if 30 minutes have passed or not. If not, then it will loop back to the top layer forecasting. And if yes, then it will proceed to the lower layer. And then I'll be handing over to my partner, Axel Ochoa, where he'll be talking about the top layer forecasting.
So, why do we need to forecast? As stated, we will be implementing the PV microgrid to power the building. That being said, there will be time intervals in which the energy generated by the microgrid will not be enough to meet the load demand of the building. At which point we need to answer the question of is it cheaper to pull energy from the battery, or should we use energy from the grid? To answer this question, we need to know how long these energy deficits will last, as well as the total energy needed in order to make up for this deficit. So our program is using two main algorithms to forecast: support vector machine and autoregressive integrated moving average, otherwise known as SVM and ARIMA respectively. For short-term forecasting, we are using SVM to forecast the load demand of our building. The input parameters are simply time, load demand, temperature, and humidity. ARIMA is used to forecast the energy generated for the microgrid. We are using ARIMA to forecast global horizon irradiance, otherwise known as GHI. We are doing this because GHI is directly proportional to the amount of energy that our microgrid will be able to produce. The input parameters for this are simply GHI and time. For long-term forecasting, we're actually using SVM for both GHI and load of the building. As you can see in the next two graphs, we're displaying the long-term forecasting of both load and GHI. The graphs are fairly accurate within some degree of accuracy, though it's pretty obvious that they can be heavily improved on. That is the purpose of the second layer of the forecasting system, which uses smaller time intervals up to 5 minutes. In order to further explain these short time intervals, I'm going to pass it on to my partner, Jose Rea.
So good afternoon, everyone. I'll be going over the forecasting for the lower layer and also the simulation results of the overall proposed hierarchical control. So first, I'll be starting with the flowchart of how the lower layer works in the PHC system. The purpose of the lower layer is to determine the output for the battery power control signal. Essentially how this will work is it first uses the state of charge results attained from the top layer, and it'll interpolate that every 30 minutes to 1 minute time intervals. It's then going to perform a weighted moving average, or ARIMA, to find the demand and the GHI, or the sun radiance in this case, for the next 5 minutes, as Axel mentioned. Finally, it will use the DPM to find the battery power of every minute for the next 5 minutes, and it will do that in a continuous loop. Next, I'll move on to the lower layer forecasting. So I'll be going over two different types of forecasting methods we tested for the lower layer. And as Axel also mentioned earlier, the lower layer is also used to help and get better and more accurate predictions. The two methods we used to see which one would give us better results are ARIMA and moving average. So here we wanted to forecast a short term of the sun irradiance for the year 2030. The graph shows a peak of 1 day of the year to display the accuracy of each method. So here the mean average error using ARIMA was around 39, while the mean average error using moving average was around 220. So the results for ARIMA are significantly better than the moving average. So I'm gonna move on to the short-term load. Here we also needed to predict the load consumption for the year 2030, since here we're also applying the two different methods. For the load, we were able to get a mean average error around 800 using ARIMA, and for the moving average, it was around 250. The results are not as low as we would have wanted them to be, but overall the moving average is better to forecast the load, and in general the ARIMA is better to forecast the sun irradiance. So next I'll be going over the simulation results of the proposed hierarchical control. So here in the PHC, or proposed hierarchical control, we can test any month of the year 2030 since 2030 is our intended goal. But here we elected to test the second week of March for both the top and lower layers, just to be consistent in the program. So in the graph, it displays the optimum state of charge in the top layer. So as you can see in the graph, it shows seven peaks of each day for the second week of March. And in the end results, it shows that the PHC can save around 20% in electricity costs. So now I'll be moving on to the lower layer results from the PHC. So here, the lower layer is simulating the battery power control signal. And as I mentioned in the last slide, this graph shows the final output of the PHC for the second week of March for the year 2030. And the final step is to use the signal and send it to the battery so that it could try to achieve optimum operation. And if the system uses the proposed hydro control, the facility electricity bill for 2030 would range around 58,000 as opposed to the 73,000 if the PHC was not applied. Or yeah. So with that being said, I'll pass it over to our lead, Jose Morales, to wrap things up.
Thank you, Jose. So to wrap things up, so for our overall project, we were able to complete the analysis system. So we were able to test and run simulations completely. We were also able to determine that SVM worked better for our top layer and our REMO worked better for our lower layer. With those two being set for each specific layer, the PHC would actually help control the battery in real time. And based on also the rest of the simulations, we were also able to determine the total cost of the system. So we estimated it to be 2.2 million. The 2 million coming mostly from the PV, and the battery size is just coming based on 183,000. Overall, I want to thank our advisor, Dr. Raj, and my team members, and also I want to thank the grad students who were out also helping us throughout the process of this project. Now, do you guys have any questions?
Okay, thank you, team. We've got some time for questions. So who would like to go first? Be sure and unmute yourself.
So Professor Thorburn, I just want to give everybody a round of applause. Thank you very much, Jose, Axel, Kajar, Co, and the other second Jose. A very nice presentation. And I just had one question. Wasn't Co going to present a chart on the optimization stuff, like the genetic algorithm and stuff? Or did I misinterpret that?
What, Cole, you want to explain it?
Which one?
I thought in the agenda that you were going to talk about the optimization. It was a small little bullet way back and maybe chart for.
No, I think that's just that's part of our agenda that we the research and the work we did throughout the semester. We didn't explain it here in this presentation. Yeah.
Okay, thank you.
Could you guys turn to page 10, please? Could you explain this chart to me? It looks like you have more PV capability than you have demand. Am I reading that right?
It looks slightly a little bit oversized, but I don't know why the graph came out to be like that, but in reality, it's not really oversized by that much.
I mean, it looks almost like you have almost twice as much PV capability as you have demand. Well, not quite, but okay.
I think it's the problem is that during the night you don't have any PV, so you have a lot of zeros. So then the peaks and valleys, when we sum it up, it's exactly equal. The problem is that during the night you don't have anything, so during the day you need to kind of overshoot and compensate for it.
Okay, fair enough.
So you need to sum across this whole chart.
Yeah, we calculate the sum. They are exactly equal. And we make them equal because we assume that building is net zero.
Okay.
Okay. Are there other questions?
Yeah, I had one quick one. I guess in looking at, I guess you can go back to page 39, which is the kind of conclusions page. I guess the basic question is that battery cost seems unusually low. Given that you're going to be load leveling, an entire facility with growth potential and things like that. I mean, we saw one presentation yesterday where the Elon Musk system was close to $1 million. So I'm just kind of wondering where you got your numbers from for the battery technology.
The battery cost was done through VPM. And that's the installation of the battery, and operation and maintenance was included is in there as well.
So that's not the purchase of the battery?
From my understanding, we basically like try to not include the actual cost of the battery into our optimization, mainly because we know that the cost of the battery is going to be a constant value that we don't really have much control over.
Yeah, and also the price of the battery is $250 dollars per kilowatt, and it's a 720 kilowatt system. And we're also assuming the prices will go down by 2030 as well.
Okay, yeah, I mean, I'd agree with that. It would be nice to, so I think that battery costs, are going to be sliding down as we convert, over to a more, electrical power, transportation grid. But I guess I would have liked to have seen your predicts on that battery cost as you kind of get down the road and begin to get into maintaining the system and maybe even changing batteries out, because those batteries don't last forever, right?
Yeah, they degrade after like 15, 16 years. And also the battery cost is included in battery sizing. Right now, as we speak, the battery prices are roughly about $400 per kilowatt hour.
Okay.
And the lifetime is also considered in the cost as well too.
Yeah.
Like you said earlier, by the time we reach 2030, the prices will go down to around 20 kilowatt hour.
That would be a real interesting question to kind of dabble around in. I mean, I know you guys are done with your project here, but when you hand this off, it might be worth writing that down as a question to be answered for the future. Because I think that's how you're going to sell this system. You're going to sell it not on the efficiency of electrical power, but you're going to sell it on dollars.
Yeah, pretty much.
Yeah, no, it's a good project. I like the work you did. Thank you.
Other questions?
Quick question for the team. So I'm actually curious. So did you guys investigate the cost of electricity for the La Cret's facility, and like what's how much does it cost for them to buy electricity, and does it depend on the time of use? How are they charged for electricity as it is right now?
Yeah, we did consider it. It's within 3 tiers. Also, one other thing is special about the building is it's LAWP owned. They don't necessarily pay the bill, but we did include the LAWP rates. Because the rates do vary throughout the day, it starts off from cheap and then it starts going up, and towards the night, it's really cheap. This building itself, since it's LAWP owned and they showcase all the new technologies and all the, cost efficient stuff that they showcase, they want to showcase this project as well to the other clients in the world.
All right, thank you. Yeah, I'm curious too. One quick follow-up for you. So with the size of the battery, so why are you not, why is the optimal here, I guess, is what I'm kind of wondering. Is this because this is where you kind of achieve net zero? Or are you a little bit bigger than net zero and it's helping you, buy energy when it's cheap and then go use it from the battery when it's,
Oh no, this graph is just for it's just the sizing of the battery itself, how it shows the optimal size of the battery, not including connecting it to the grid.
Okay, so it's not connected to the grid, but it must have some interplay, I would assume, with the time of pricing, right? Like that would affect, because this having a battery or not would affect if you're buying electricity or not, I assume, at certain times, right?
Yeah,
Yes.
and also because since the battery is larger too, it's less energy and more power, but the installation cost is more as well when the size of the battery goes up as well.
Got you. So that's keeping you from getting bigger, is this installation cost.
Yeah.
All right. Thank you, team. Yeah, really some cool charts and a lot of cool different work that you guys did on the project.
Okay, if there are no more questions, we've got just a few minutes before our next presentation. Let me thank the optimal design and control of a hybrid PV system team and their advisor. Thank the audience for participating. And let me remind the audience that we've got Qualtrics surveys for you to fill out to provide some feedback to the team and to me about the program. Okay. Our next presentation will start in, approximately 7 minutes or so. This will be the low-speed crash test system. As soon as you got your whole team here, we've got just a minute or so, but we're about ready to go.
You said nobody else is trying to get in right now because our last team member is messaging us saying he's still trying to get in.
Well,
his name is Rene Flores.
I don't see him. Maybe is he trying to get in a different meeting?
Let's see.
Don't see him on the list. We've got 38 people in the room, but we've had as many as 65 today earlier. So, shall I send Renee the link?
I just sent it to him on. I just sent it through message.
Okay. Here he is. Okay. Okay, so somebody on the team can take over the screen. Yes. Excellent. So welcome everybody to Expo 2020. This is the final presentation for Tuesday, Cinco de Mayo. We've got a full slate of presentations Wednesday through Friday from 2 p.m. until 6 p.m. every day. We've had great participation. I'm sure the next presentation will be equally as interesting to hear about. I do welcome everybody's comments. We've got a Qualtrics survey. You have the links to it. I'll post the link again in the chat room so that if you can't seem to find it, you can then find it. I encourage you to take a moment and fill out the survey at the end of the meeting. Your opinions, they do matter. There'll be good feedback to the students and good feedback to me. Okay. Without then any further delay, here's the development of the low nitrous oxide natural gas burner team.
Hi everyone, this is Team 70. Our project is a continuation of the development of a low NOx natural gas burner. Our advisor is Professor Jeffrey Satner. The project is sponsored by Sempra Energy. The members of this team are myself, Ethan Blancio, George Majano, Brian Rodriguez, and Renee Flores. First, I'm going to go over the background. Combustion processes have been, are, and will be for the near future the prime generator of energy in our civilization. This energy allows us to produce heat through the ignition of fuel and air. The processes must be managed well for the sake of the environment and the sustainability of civilization. Our project deals with the combustion of a hydrocarbon fuel, methane, and air using a cooking burner. From a general combustion equation that involves air and methane, ideal products are produced from this chemical reaction: carbon dioxide, water vapor, oxygen, and nitrogen. However, that is not the case. Combustion has consequences in the form of pollutants such as carbon monoxide and nitrogen oxides, also known as NOx. High levels of NOx pollution create environmental and health hazards which can lead to acid rain, smog formation, and respiratory illnesses. By minimizing NOx emissions, health and environmental hazards will be reduced. To understand NOx, I will now go over where it comes from. Combustion involves the burning of fuel and air. The composition of air consists mostly of nitrogen, as shown in this pie chart. Nitrogen is a diatomic molecule with strong triple bonds. When the temperature is high, there is enough energy to break this molecule. The formation of NOx is produced through this concept. Under ideal situations, NOx isn't formed. Realistically, high combustion temperatures increase thermal NOx, which can be described by the two chemical reactions known as the Zeldovich mechanisms. The Zeldovich mechanism shows that nitrogen atoms at high temperatures break apart to combine with oxygen atoms. This reaction results in the production of nitrogen oxides. Equivalence ratio is a quantity used to determine whether a mixture is lean or rich. It is described by the desired air-to-fuel ratio over actual air-to-fuel ratio. An equivalence ratio greater than 1 produces rich mixtures, where an equivalence ratio less than 1 produces lean mixtures. From the graph, lean mixtures are found on the left-hand side of the dotted line. It shows that nitrogen oxides peak at leaner mixtures, while carbon monoxide steadily increases. We don't want to run rich because as the mixture becomes more rich, carbon monoxide continues to increase, which is a more deadly pollutant in comparison to nitrogen oxides. Therefore, we must produce a lean mixture so that there will be less NOx emissions, as well as minimizing as much carbon monoxide as possible. The main goal of our project is to reduce NOx. There are NOx control strategies in place by various industries, though it is not in place for cooking burners. Manufacturing industries use chemical scrubbers. The automotive industry uses catalytic converters and exhaust gas recirculation. For the purpose of our design, we will attempt the exhaust gas recirculation strategy. Exhaust gas recirculation, or EGR, is the process of redirecting gases burned from the burner back into the combustion chamber to be burned again. An EGR system not only redirects exhaust gases, but it helps to reduce the peak temperature of a flame by reducing the energy available for the reaction to create more NOx. Now George will go over the objectives.
The primary goal of our project is to reduce NOx emissions by at least 50%. To do this, the first step would be to seal the combustion chamber and implement a controllable air supply into the system in the form of a pump. In addition, part of the exhaust gas will need to be redirected back into the combustion chamber through an EGR system. Finally, NOx emissions should be measured before incorporating the EGR system and after to determine the effectiveness. These are the key characteristics the system should have. To premix the methane and air going into the system, the air-to-fuel ratio needs to be adjustable. The EGR system should recycle up to 20% exhaust gas, as this can reduce NOx emissions by up to 70%. Power usage should be kept low, with voltage topping out at 12 volts. Electronic control should allow pumps to have variable output range. The exhaust gas being recirculated should be cooled to below 50 degrees Celsius to stay within the EGR pump's operating temperature. And finally, NOx should be reduced by at least 50%. As mentioned previously, this is a continuing project, and this is a prototype of the first senior design team built. They designed a seal system that was driven by a compressed air tank and a methane tank, which allowed them to research premixed combustion. Once the proper stoichiometric ratio was achieved, the gas will be moved to the combustion chamber to be burned, and the exhaust transferred to a gas analyzer. Our goal is to incorporate an exhaust gas recirculation system into this design. Prior to testing, Cantera was used to find an optimal equivalence ratio of 0.75 with a minimum 15% recirculation of exhaust gas, which can be seen from this graph. The equivalence ratio of 0.75 can be seen in blue, with the red line being the upper limit of where we want our NOx emissions to be, with the bottom axis showing exhaust gas being recirculated. The dotted line shows the equivalence ratio crossing the upper limit at about 0.15 or 15%. Next, I'll be talking about our current design. Our design, which is currently shown, is meant to incorporate directly onto the existing prototype. The first goal of our system is to eliminate the need for compressed air, so we are introducing an air pump that brings in ambient air in its place. This will run at a specified voltage to have it match the air-to-fuel ratio required based on the flow of methane going into the system. This will create a premix that has an equivalence ratio of about 0.8. As a precaution, a check valve will be added to the methane inlet that will close off if the back pressure gets too high. After combustion, the exhaust gas will be redirected through a heatsink to be cooled to below 50 degrees Celsius. The EGR pump will then redirect it back into the system where it will help reduce the peak flame temperature. Brian will now talk about how we will control flow rates throughout the system.
We mentioned the equivalence ratio earlier, and how if we stay in the lower range of around 0.8, NOx and carbon monoxide would be reduced. The burner we were given is rated at 12,000 BTU. From this, we were able to obtain the mass flow rate of methane produced. Using the equivalence ratio, along with the methane mass flow rate, we calculated the required amount of air flow rate to produce the ratio we wanted. We aimed to recycle 20% of the input gases because we found it to be a value that may reduce up to 70% NOx formation. After this, our task turned to procuring devices that could provide these results. We were able to find low voltage pumps that were within our flow rate ranges and were meant to run for long periods of time. Unfortunately, we had a problem with the devices that I'll discuss shortly, but ultimately we were forced to scale down the system to 24% of what we originally planned for. We needed to calibrate our pumps to determine the actual flow rates produced so that we could integrate them into our system. We used a volumetric flow rate reader called the MATLAB's Defender Series 510 to accurately determine the flow rates produced. We were working with really low flow rates, so it was important and necessary to have a low flow volumetric flow rate reader. We were able to find a small 12-volt pump online to supply the system with air with these specifications. The pump had several characteristics that met our requirements. It was advertised as a low power operating device with a flow rate of up to 1.4 CFM and it had the size outputs we were looking for of about 1/4 inch. We used the volumetric flow rate reader to determine the flow rates produced, and we were able to reach 0.59 CFM. This is the reason we were forced to scale down. Another thing to notice is our device's stability diminished after 8 volts. The details of our EGR pump are similar to the air supply pump. We purchased a low voltage operating pump with a determined max flow rate of 0.248 CFM. The inlet and outlets also match what we wanted. Based on recirculating around 20% of exhaust fumes, we determined that such a flow rate would occur between 4 and 6 volts. One key difference between the EGR pump and the air supply pump is we must take the temperature of the exhaust gases into consideration. The maximum operating temperature of the pump we purchased was 50 degrees Celsius. Because of this, we needed to develop a way to reduce the exhaust gas temperature so it would not burn out the pump. We'll talk about this development in later slides. Here we are showing how the effects voltage has on mass flow rates of the pump and on the equivalence ratio. Remember, stoichiometric air to fuel ratio is determined by the molecular weight of air and fuel. So the flow rates of each input play a big role in the equivalence ratio. First, I'll explain the mass flow rate of air, which is denoted by dark circles in the graph. Again, if we increase voltage, we'll increase the mass flow rate up to a point where the device becomes unpredictable. This point occurs at a voltage of 7.5, which we have highlighted on the graph. The other set of data points plotted are the equivalence ratio determined as a function of voltage applied to the air pump. At the maximum flow rate produced, we were able to obtain an equivalence ratio just under 0.8. Our devices will provide a certain output of flow rate depending on the voltage supplied to them. We were required to find a method to regulate the voltage so we could set each device's flow rates to match the requirements needed for an equivalence ratio of 0.8. We searched for various methods to accomplish this, including using potentiometers. We found this variable resistor or decade box to be the easiest to purchase and use, as well as provide accurate and consistent results. If we went with a potentiometer, we would have had to measure the voltage across the system every time it was adjusted, whereas this decade box, we could measure once and create a table that tells us the correlation between applied resistance and the flow rate. Here we show a diagram of how we implemented the decade box, as well as the full electrical layout. We set our devices in a parallel configuration so that they could get a max of 12 volts supplied to them. This way the air supply pump could run at its maximum and we could adjust the EGR pump's power by applying the resistance in series with it. That's where the decade box comes into play. We used Kirchhoff's voltage law to determine the resistance we would need to get the EGR pump to a certain voltage. We were able to build the wiring harness and get it operational, but the remaining step was to just calibrate the resistance to correlate it with voltage. Renee will now go over those thermal controls.
So recalling that lowering peak flame temperatures lead to lower thermal NOx formations, we designed an annular heat sink unit to dissipate heat from the recycled exhaust gases before allowing them to flow back into the EGR pump. If implemented properly, cooler gases would prevent thermal damage to the pump, in addition to improved heat absorption from the combustion flame. We decided to use aluminum 6061 because of its high thermal conductivity and good machinability. So using fin efficiency equations in combination with optimization techniques, we wrote a MATLAB script which would determine the optimal fin thickness and fin radius of our heat sinks. These results are shown on the graph to the right. The solid blue and black lines are essentially the boundaries of our best design variables with the given constraints from the table to the left. The dimensions we seek are essentially found between those two lines. We also have to observe that the green lines, the contour lines, are decreasing in the left direction. So these lines represent the total fin volume of the entire unit. So to save on material costs, we would choose a value that would lean towards the left side of the graph. And our optimized solutions are displayed there as 3.2 centimeters for the outer radius of the fin and 4 millimeters for the fin thickness. So on the left hand side, we see the blueprint for our unit, for our optimized unit. The interior of the tube was expanded in efforts to add additional surface area for heat transfer. And due to its cylindrical design, manufacturing of this unit will simply require the use of a lathe, as shown on the video on the right. So we also performed thermal studies on the fin unit. We essentially assumed that 5% of the 12,000 BTUs at a time length of about 20 minutes were applied in the interior of the fin, in the tubular section. We also did a simulation with 10% of the 12,000 BTUs, and because our pump had to operate under 50 degrees Celsius, we had to use this conservative value to determine if the fin would remain below this number. So as the videos show, the temperature of the fin remains relatively close to room temperature towards the end for both the 5% and the 10% unit. And then we also tried to simulate the flow of the exhaust gas passing through the heatsink unit. We researched that exhaust gas for natural gas would be about 180 degrees Celsius. So we modeled our airflow going into the unit as such, which is the 453 Kelvin. We're looking at we can see from the cup plot from the left that fluid exits at about 46 to 56 degrees Celsius. So this is close to the operating temperature of the EGR pump. The cup plot on the right simply shows the behavior of the exhaust gas in the expanded region, as well as the temperature profile of the surrounding air from the natural convection. And from the video on the left, we can see the fluid deceleration and rotation at the entrance, which was an added benefit of our design if we desired to maximize heat transfer before having the fluid exit the unit. And so for our project status, items 1 through 3 were completed. However, due to the virus epidemic, we were unable to continue testing and machining of our components. On the right is our design setup, which doesn't include the annular heatsink and without the electrical control mounts. We therefore focused more on simulation studies, design improvements, and considerations for next year's senior design. And now we'd like to thank Dr. Santner for advising us and guiding us throughout the entire year. Dr. Deperdinis for helping us with refining our MATLAB script code, and Dr. Park for his lectures on optimization techniques, and Sempra Energy for sponsoring our entire project. Any questions?
Okay, well, thank you very much, team, for an interesting presentation. We have all the time in the world for questions. This is the last presentation of the day. So who wants to go first? Let me ask, the simulations that you did, what was the computational platform that you used? Were those done in Simulink or in?
Those, for the thermal simulations, they were all done with SolidWorks thermal analysis and for SolidWorks Flow.
Okay. Other questions?
Oh, so I'm kind of curious. So I guess I like a lot of the kind of the simulations you did and the concepts. It looks pretty good. So you're essentially making your flame temperature colder by losing heat over here in your heat sink. And so, you know, I guess kind of like two questions. Like, do you think there's gonna be an issue in that, like, when I have a burner, I'm gonna be kind of upset because I have to use more fuel to heat up the same amount of food? And maybe is there a way to, like, you know, could you maybe find a way to use that heat for something useful? Maybe not in the flame, but, you know, maybe I could have like a coffee cup warmer or something on the side of my burner, you know, something, you know, I'm just trying to think, what are some ways where you could use this heat and not just waste it into the environment?
Well, we're not trying to lower the overall temperature. We're just trying to lower the peak temperature. The thing is, we still have to test it, but we should have overall the really similar heat output. But like I said, we just want to lower the peak temperature.
Got you. And what do you mean by peak? What do you mean by peak? Is it like vary in space or vary in
it varies
vary in
within
time?
the flame itself. Usually, like in this case, it will be almost like a shape of a triangle coming out of the burners, and at the center of the triangle will be the peak temperature, and we want to reduce that peak temperature.
Got you. But you think it'll only have an effect on the peak? It won't have an effect everywhere in the flame?
Well, that would be something we'd have to test.
For the most part,
I don't envy that. Sounds like a hard test, but it'll be really cool. It'd be really cool to see the flame temp throughout the flame. That'd be some cool stuff.
Yeah, we had difficulty. I was looking into like seeing if we can find a thermometer that we can use to measure the flame at different sections of the flame. But some of them have to be. I think if we're working with high temperatures, some have to, like the ones that have the temperature range have to be used in like a vacuum environment. So it's also like the material, like we want to measure if the high temperatures, but the materials that are available for that are not practical in this design. But yeah, we thought about trying to measure those, at least the flame temperature, and see if there are significant differences. So.
Also, to add to that, the prototype, it wasn't pictured, but the lid does have thermocouples throughout the whole lid to measure the overall output.
So I'm curious, what kind of problems or issues did you come across when you were trying to kind of determine what the the optimal fuel to gas mix was going to be? I mean, was that just kind of trial and error, or did you do a parametric study, or how did you ultimately figure it out that the mix that you were going to use was the right one?
Well, as stated, we did do research, and we also did go based off of last year's senior design team. They ran a Cantera simulation, trying different mixtures and finding like what would be the best stoichiometric ratio. And like I said as well, we did do research for that as well.
Yeah, I might have missed it, but how difficult was that to ultimately achieve in real life? I mean, did you have to play around a lot to just sort of dial it in, or was it kind of a first attempt? You got it and it looked good.
Well, like I said, this was in the testing phase, so we didn't actually get to see how stable the flame would be at different equivalence ratios, but it's something that we were looking into.
Yeah.
Yeah, there's a combustion research team that's looking into that, to testing out different equivalence ratios, and I think the same what you're asking, the flame stability. And
Yeah.
so our project was basically gonna converge with theirs, and we would add the EGR and see how that would affect their research. So
It'd be a curious study to look at, like burner configuration or the way typical gas burners look on stoves. Is that the ultimate, is that the optimum design, or should they look different? Should they look more like a flame pan on the end of a rocket, or, what would make the difference? I'm just kind of a curious question.
So I believe there is a research team also working on similar to this project. We're mostly focused on the exhaust gas recirculation method. There is another team, however, working on just that, testing out different burner configurations.
Yeah.
So mainly our focus wasn't on that, but it definitely would play into account.
Yeah, no, recognize that, but it's just definitely something that's got a strong component to what you're doing. Yeah. Cool. Good work.
Thank you.
Thank you.
Yeah, I like playing with fire.
Just one quick question. Have you tried to boil the water without or with EGR?
No, not yet. We're still testing to see if we could get the stability of the flame going.
And the reason that I'm asking is this, because if you just without doing the EGR, it takes 10 minutes to boil the water. But if you're using with the EGR, it takes like 15 minutes to boil the same amount of water.
Right.
You're gonna be really, saving the earth in terms of NOx. That's the thing that I'm.
Have there are thermocouples attached to the lid, so that would measure how much heat output the burner is producing before attaching the EGR system and after.
So you did test it?
Not with water, but
I mean, just using the thermocouple. The water was simply a example.
yes, it is part of the testing as well.
So it was a constant heat out without it. So effectiveness is much higher than in terms of the NOx.
We still haven't gone to that testing phase, but it is going to be part of the test itself.
Oh, okay. So after you finish the core product, you're going to test that and then figure out that aspect as well.
All right.
Okay. Thank you.
Thank you.
Thank you.
Okay. Any other questions?
I got another one too. So I saw that I saw some machining, but I never got to see the I didn't realize how big it was first. I never got to see the final product. Is it halfway done, or you just
no? We were pretty much halfway to the reduction of the outer diameter to the fins, but cutting like between the spacing of the fins, we didn't really get to that portion, and to drill out the interior of the unit. So it was what we learned. Well, at least what I learned is that it's a really long process to cut across like longitudinally of the unit. So because there's only a certain amount you could feed in there at a time, and with the automated lathe that moves fairly slow, it took some time. So I mean, after everything got shut down, we couldn't really move forward with that.
Totally understandable.
But
you can tell
we got
Cody
plans.
suggested he finished it after you're done.
Yeah.
Okay. Other questions? If not, congratulations to the team. Thank you very much for the presentation. It was very interesting. I want to thank the audience for hanging in there with us today, and to encourage all of you to come back tomorrow and every day the rest of the week, from 2 until 6 for the rest of the expo. Don't forget to fill out your Qualtrics surveys, and give me a call or drop me an email if you have any questions.
All right. Thanks a lot, Mike. Good session today.
Thank you.
Thank you.
Thank you.
Yeah, good work, team. Really cool stuff.
Thank you.
Thank you, Paco.